We have discussed last class regarding signal classification. I told that signals can be classified into two types, that is continuous time signals and discrete time signals. This time happened to be the independent variable that we have considered to represent some sort of importance. So if there happen to be infinite possibility between a given bound of time, we used to call that type of signal as continuous time signal. And if there are uh, discrete values in between a given boundary of time, we used to call it as discrete time signals. And another way of classification we have seen, we used to classify as analog signals, and we used to classify as digital signals. And I told that if y-axis happen to be continuous, that is the dependent variable axis happen to be continuous within a given boundary, we call it as analog. If the dependent variable axis within a given bound is capable of holding only finite set of values, we call it as digital signal, right? So I had given an example of M array signals where this capital M represent the number of levels that are present in the independent variable axis. And I told that if the value of capital M is equal to 2, we call it as bi-array, or we call it as binary signals, right? So which can be represented as either low or high. So another way of classification we will study now. Signals can also be classified into two types. Uh, One type is called as deterministic signals, and another type is called as random signals. So deterministic signals means what? We can predict the behavior of the signal. Like there might be some formula. Let's suppose, let's take an example: y is equal to mx plus c, and I take this as x-axis and I take this as y-axis. And let's suppose we have equation of a straight line, y is equal to mx plus c. So for various values of x, we can predict the value of y, because we know there is a formula here, right? So this type of signal is called as deterministic signal, where the signal behavior or the uh, dependent variable value can be calculated based on some sort of mathematical expression, right? Such type of signal is called as deterministic signal. And where the uh, amplitude axis or the dependent variable axis is behaving randomly with respect to the independent variable, that sort of signal we call it as random signal. Example is, uh, let's take a electrocardiogram signal. So if at all when you visit to hospital, or you see the screen of a electrocardiogram display, so where the different pulse rates of heart, they are displayed. Let's say this is the screen, and on the screen you can find some sort of waveforms like this. Okay, sometimes there are spikes. So the behavior is random, isn't it? The behavior of the signal is random. Sometimes there are spikes, and sometimes it is the variance is less, right? This is an example of a random signal. So in communication, or in the electronics and communication engineering, most of the time we will be dealing with such type of signals. So it is difficult to predict the behavior of the signal. So we need statistical models and other estimation techniques to learn the behavior of this model, and we need the concept of probability and statistics. And we call such type of the signal analysis as a random process, right? We call it as random process, and using those sort of technique, we uh, calculate the necessary things for analysis of these random things, right? The first one is deterministic signal, which we are going to learn many aspects in this course. Right? Deterministic signal can be mathematically expressed properly, and the behavior of the signal can be predicted based on the mathematical equation that we have. It can be easily mathematically expressed, right? Whereas random signal cannot be expressed easily using mathematics. Now we have to take some random behavior or statistical way to represent them and to analyze the signal behavior, right? So we have learned three type of signal classifications. You can see signals that can be classified as continuous time and discrete time signals, signals that can be classified as analog and digital signals, signals that can be classified as deterministic and random signals. Few more type of classifications we will study time to time. I mean, in the coming classes, signals can be classified into energy signals and power signals, signals that can be classified into even or odd type of signals, or periodic or aperiodic signals. There are various classifications based on various parameters, right? So here we have taken for the first case, signals can be classified into two types based on the independent variable, uh, based on the values of independent variable. This is based on the values of dependent variable. So here, uh, based on the type of, you can say, signal behavior, right? It can be either deterministic or random. So today we will see, we will pick some sort of continuous time signal and discrete time signal, and we would like to see mathematically what we can do with them, like amplitude scaling, time scaling, or we can uh, flip the signal, right? Or we can add some signals, we can multiply some signals, we can subtract some signals. So let's take few examples and try to understand, right? So signal behavior uh, for continuous time and discrete time simultaneously we will see. Okay, so let me take addition of two continuous time signals. We would like to add two continuous time signals. So how a continuous time signal can be represented? I told you that we need some function name, and we need to write the independent variable inside a bracket. So this can be one signal. So let me write x1 of t is one signal and x2 of t is another signal. So I will write, let x1 of t and x2 of t are two continuous time signals, and I would like to uh, write the signal behavior mathematically, and let me write x1 of t. It can be mathematically expressed, or the value is, let's suppose, 2, where for t lying between 0 to less than equal to 1, and the value is 3 when t lies between 1 to 2, right? And we can write, let's say the value is 1 when t lies between -1 to 0, and the value is 2, -2, let's suppose, when t lies between -2 to -1, right? So this is the mathematical expression given. So when such type of mathematical expression is given for a signal x1 of t, so how to plot it? How to plot this signal? How to plot this signal? Let's see. We will take two axes, x-axis and y-axis. So let me show you how we can draw it. So let me take, I have taken one x-axis. Okay, x-axis happen to be time, isn't it? So it is shown here in the question that the independent variable is time. And let's go for the y-axis over here. And I'm marking the points over here. So x-axis is time, y-axis here I got x1 of t. This is the amplitude. So let's suppose this is 2 points that do represent. Let's say the value is 1 here. Value is 1 here. It's 2 here. It's 3 here. Similarly, take this is -1. This is -2. This is -3. Right, and on the x-axis, I'll take this is 0. This is t is equal to 1, t is equal to 2, t is equal to 3, 4, and so on. This is -1, -2, -3, -4, and so on up to infinity. So we would like to plot x1 of t, and the mathematical expression of x1 of t is given here, isn't it? So these all are the mathematical expression of x1 of t. So how to plot them, right? How to plot them when this mathematical expression is given? So let's try. So the first behavior you can see here, when t lies between 0 to 1, right? T lies between 0 to 1, the value is 2. In between 0 to 1, the value is 2. Now, when t lies between 1 to 2, the value is 3. The value is 3 from 1 to 2. And when t lies between -1 to 0, the value is 1. -1 to 0, the value is 1. So this value is 1. It is -1 to 0. And for -2 to -1, the value is -2. -2 to -1, the value is -2. So this is our signal. And for other values of time, the value is unknown. So this yellow colored one that you see, that happened to be our signal x1 of t. That happened to be our signal x1 of t. Right, which exist from -2 to t is equal to -2 to 2. And you can see in between t is equal to -2 to 2, for each and every value of time, there happened to be one y-axis value associated with it, right? So it happened to be a continuous time signal. Now we have one signal like this, and let's take another signal x2 of t and mathematically express it. Let me take x2 of t. So
Excuse me, sir.
yes.
Sir, in that graph, how can we take that signals as continuous, sir? When t is equal to 1, we have a y coordinate that from exit from 2 to 3 now. So for single
Yes,
value of 1, how different values of y can be exist? So that can't.
it is visible like there is a straight line, but practically at t exactly t is equal to 1, we are having only one value, single value, right?
Yes,
So in between 0 to 2, if I take thousand of values and represent them, okay, In between,
Yes,
let's
sir.
say 0 to 2, I take thousand of values, 0, 0 0.001, 0 0.002. So the neighboring values will be quite similar with the previous one, right? The
Yes, sir.
immediate neighbor. So it is not an immediate transition from 2 to 3 that you see here. Okay. So later we will study that there is some delay in between transition from 2 to 3, right? If you maximize this figure, you will find that for a given instance of time, there is a one specific value associated with it, right?
Yes, sir.
So,
Thank you, sir.
so x2 of this is for just understanding I have taken. That's why I have written here for t 0 to less than equal to 1, we take this, and from when t is greater than 1 and less than equal to 2, the value is 3, right? So at t is equal to 1, the value is 2 only. Understand? At t is equal to 1, the value is 2 only. And
Yes, sir.
when
Understood,
t
sir.
is greater than 1, the value is 3, right? But it's visible like this to us. Okay. We have only unique value associated with each value of time, right? Based on the equation given. So let's suppose x2 of t also I take in similar way, and let me write the value when t lies between 0 to 2 less than equal to 2, I take the value to be 3, and when t lies between -2 to 0, I take the value to be -3. And this is the mathematical expression given. So how to plot this x2 of t? How to plot this x2 of t? Let's take x-axis and y-axis and represent it. So let me take it here only. So this is the y-axis that we have, and let's go for the x-axis. This is the x-axis I have, and let me represent these values. So I take it as 1, I take it as 2, take it as 3, take it as 4, and on the y-axis, this is, let's suppose, -1, this is -2, this is -3, and this is -4. Okay, and this intersection point is 0, and in the time axis, this is time. Always do represent y-axis and x-axis first. So this is time. So let's suppose this is 1 second, 2, time is equal to 3, time is equal to 4, time is equal to 5, and here I take -1, -2, -3, -4, -5, so on. Right? Now, what is given mathematically in the signal expression? x2 of t is 3 when t lies between 0 to 2. Right? So when t lies between 0 to 2, the value is 3. So let me plot it. The value is 3 when t lies between 0 to 2. And when t lies between -2 to 0, the value is -3. So this is the signal behavior that we have, that is mathematically represented, and we have plotted it, right? Let's see. Okay, so this is x1 of t, right? This is x2 of t. Now, if we would like to add them, if we would like to add x1 of t and x2 of t, so how and what will be the answer, right? what will be the answer. So let me put it on the same axis. So let me take x-axis and y-axis similar way so that we can understand easily. So I've taken y-axis. Suppose we have the x-axis here. So as usual, the x-axis is time, and we are interested to find out x1 of t plus x2 of t. Right? So x1 of t plus x2 of t. So let me represent this signal as x3 of t, that is equal to x1 of t plus x2 of t. We are interested to find out this, and we would like to plot it. Right? So let's see. Now for t is equal to 0 to 1, for t is equal to 0 to 1, you can see what is the value of x1 of t for t is equal to 0 to 1. It is minus 2, isn't it? This one, it is minus 2. So this is minus 2 and this is 3, right? This is 3. So minus 2 plus 3, how much? Not minus 2, this is plus 2, right? Plus 2 plus 3. So it is 5. So for t is equal to 0 to 1, let us name it or put the index in 0. This is 1, this is 2, this is 3, 4, 5, 6, and so on. Minus 1 second, minus 2, minus 3, minus 4, minus 5. So let me write it as 2, 4, 6, 8. Just I have changed my scale. This is minus 2, minus 4, minus 6, so on. So one is in mid, I mean this middle value is 1. 1, 2, 3, 4, 5, 6. Okay. So what will be the answer? If you add these two signals, then visualize this is 3 plus this is 2, 3 to 5. So at 5, we will from 0 to 1, we have the value 5. So we have the value 5 from 0 to 1. Now from 1 to 2, what is the value? 1 to 2. When t is equal to 1 and greater than 1, less than equal to 2, the value is 3 for x2 of t, and here also the value is 3. So the answer will be 6. Right? The answer will be 6. And for the negative side of t, you can see this is from minus 1 to 0, that is plus 1, and this is minus 3. Plus 1 minus 3, it is equal to minus 2. So it will be equal to minus 2. This will be equal to minus 2. And when t lies between minus 2 to minus 1, this value is minus 3, isn't it? And this value is minus 2. Right? This is minus 2. So the net value will be around minus 5. So minus 5 will be somewhere here. Okay. So this is the signal x1 of t. This red color one that you see, this is x3 of t. Right? This is x3 of t. That is equal to sum of x1 of t plus x2 of t. So what will be the mathematical expression for x3 of t? I write here x3 of t. Can anyone say?
-5.
Let's write from when t lies between -2 to -1. What is the value?
-5.
-5. And when t lies between -1 to 0, it is
-2.
-2. And when t lies between 0 to 1, it is equal to
5.
5.
5. And when t lies between 1 to 2, it is
6.
6. So this is the mathematical expression that we obtained uh, for the signal x3 of t, which happened to be sum of these two signals. So we had taken x1 of t as one continuous time signal. This is one continuous time signal. x2 of t happened to be another continuous time signal. And we have added two continuous time signal and got the result as another continuous time signal. In this way, signal addition for continuous time signal is done. Right? Similar way we can do for the discrete time signal. Okay. Similar way we can do for the discrete time signal. So let's represent discrete time signal. So I told you how discrete time signal is written. Can anyone remember? Like continuous time signal, we write it as x of t. Discrete time signal, we write it as x of
N.
X of n.
nts. X of nts. Right? X of n happen to be discrete sequence. Right. So let's write discrete time signal. And discrete time signal, we represent it as x of nts. This t is replaced by nts, right? So for continuous time signal, the expression was x of t, and for discrete time signal, x-axis is discretized, right? So t is replaced by n into ts. Right? T is replaced by n into ts or n into t, whatever you say. I have taken the subscript s here to represent sampling interval. I will tell you what do we mean by sampling. I told you that to convert continuous time signal to discrete time signal, we use one method called as sampling method, right? So after sampling the signal, we get the discrete time signal. Okay, so let me take one small example here. So I have, let's suppose this is time axis and this is, so the y amplitude axis, and let's say this is as well 1 2 and this is 3, and I have a signal like this. Okay. So I have a signal like this. This is 0, this is 1 2 3, e is equal to 1 2 3, this is -1 -2 -3. Right? This pink color line that you see, that happen to be the signal. So what we can say, the signal that I had written here, let's suppose this is x of t, this pink color one is the x of t, and it's looking like a triangular signal, and we see that for every value of time this pink color signal exists, right? So this is an example of continuous time signal. Now what we will do, we will take 6 samples out of it. We will take 6 samples out of it, 6 or let's say 7 samples out of it. Right? We take 7 samples out of it, and we would like to uh, see how we can get the discrete time signal. Okay, so let me this figure. Okay, so here what I will do, let me plot it in another color. I'm interested to sample this pink color one and consider the discrete version of it. Let's say at 3, I am taking one sample and the value is 0. At t is equal to -2, I am taking a sample and this is the value. At t is equal to -1, I'm taking a sample and this is the value in the figure. Right. So here is one value. I have taken another sample here. I have taken another sample here, and I have taken another sample here, and we have taken one sample here, taken one sample here. Right. So how many green color lines you see in this figure?
7.
7, right? The pink color line indicate the x of t, right? Pink color line indicate x of t, that is the continuous time signal. And I used a method and I sampled the x of t signal, or the signal x of t is sampled at a given rate, fixed rate, and 7 uniformly spaced samples are taken from x of t, right? You can see 7 uniformly sampled signal. What do we mean by uniformly sampled? You can see what is the time difference between first sample and second sample. It is, what is the time difference? -3 to -2.
1 unit.
1 unit, right? It's 1. Similarly, -2 to -1. What is the time difference between these two samples?
1 unit.
Right? So similarly, you can see the time difference between two successive samples, they are same, isn't it?
Yes, sir.
Time difference between two successive samples are same. So that's why we call this signal, this pink color signal, which happened to be continuous time signal, is uniformly sampled. Uniformly sampled. So for this uniformly sampled signal, right, this green color signal, this green color one, they are called as discrete time signal, right? Discrete time signal. So what is this 1 unit? This 1 unit, let me take it as the sampling interval Ts. So what I will write when I plot this green color signal, okay? So let me take it here. This is the time axis T, and this is the y-axis, okay? And let's take y-axis in some other color. This is the y-axis, and this is the x-axis, right? So I would like to plot the signal, this discrete time signal. So at 0th second, t is equal to 0, what is the amplitude? It's 3, right? The amplitude is 3, and at t is equal to 1, so let me write it as ts. T is equal to ts. I have taken the sample after ts second, right? So the ts value is 1 here. So at ts second, what is the amplitude? It's around you can say 1.7. Okay, it's not exactly 2. It's around 1.7 or something like that. And at t is equal to 2 ts, after another ts interval, like you can see it's around 0.9 or something. Okay, and at t is equal to 3 ts, it's nearly 0, right? It's nearly 0. Similarly, at t is equal to minus ts, the value is around 2 point like 1.7 something like that, and at 2t minus 2 ts, the value is around 0.9 or nearby 1, and at minus 3 ts, You can see it's 0. Right? So this green colored signal, this is what your x of nts is, right? So you can see x-axis at 0th second, after ts second, after 2 ts, or after 3 ts, we have samples. We have samples at regular interval of time, and we can say that this discrete time signal is having uniformly spaced samples, right? It is not mandatory that always discrete time signals will have uniformly spaced samples, but for processing it is easy if we have uniformly sampled signals, right? So in textbook you will find that this is represented as x of n, right? X of n. Why? If I remove the notion of time here, if I remove the notion of time here, let's suppose you can see this ts, what I can write, this ts, I can write it as this is 0 into ts, this is 1 into ts, this is 2 into ts, this is 3 into ts, this is minus 1 into ts, minus 2 into ts, minus 3 into ts, right? So if I remove the notion of time here, and if notion of time is removed, I am left with only indexes, right? I am left with only indexes. So it won't be t anymore if I remove the notion of time. And let me put it in this way. So if this happened to my x-axis, and I removed the notion of time, and this 0, 1, 2, 3, I take index n, and I write that when the n value is 0, and the index when n value is 1, the n value is 2, n value is 3, or here n value is minus 1, minus 2, minus 3. So what is my y-axis value, right? What is my y-axis value? So when it is 3, this is 0, and when it is 2, let's suppose the value is around 0.9, and when this is minus 1, the value is around 1.8 or 1.7, and when t is equal to 0, the value is around 3, and at n is equal to 1, the value is around 0.9 again, and n is equal to 2, sorry, at n is equal to 1, let's say this is around 1.8 or 1.79. Here it is around 0.9, and here it is around 0.1, let's suppose nearly 0. So this is represented as x of n, right? Here I have removed the notion of time. X of n is called as discrete sequence. It is not discrete time signal. It's called as a sequence. Always remember, stating x of n as discrete time signal is wrong. Discrete time signal, when we speak time, there should be some time over here. X of n is called as discrete sequence. So this can be mathematically represented how? So let me write x of n, and I can write it as like this: 0 0.1, 0 0.9, 1.8, 3. Okay, and with a comma also you can write 1.8, 0 0.9, 0 0.1, like this. But if you write like this, we are missing here something. We don't know where is the where is the 0th index, right? So the what is the first index we cannot comment. So if you are given x of n like this, someone may take this is 0th index, this is first, this is second, third, fourth. So you will get a right-sided signal, right? So we have to mandatorily show the index. So what we have to do, where the 0th index is there, we have to put an arrow mark. Right? We have to put an arrow mark below it. This is expression of a discrete sequence. This is the representation of a discrete time signal, and this pink color one is representation of a continuous time signal. So when we what method we use to get this green color one from this pink color, that is called as the sampling method.
Sampling.
Right? So using sampling method, by taking uniform samples out of the continuous time signal envelope, we get the discrete time signal. And if we remove the notion of time from the discrete time signal, we are left with discrete sequence. So in our course, mostly we are going to deal with these sort of discrete sequences and continuous time signals, right? So when notion of time is removed from discrete time signal, we call it as a discrete sequence. That is represented as x of n, y of n, whatever, right? Based on some index. So here there is no notion of time. Notion of time is removed. Okay, it helps in easier signal processing and makes our life simple when we go for mathematical models, etc. Right? So I guess whatever we discussed today is clear to all of you. So we will stop at this point of time and we'll meet again on Friday, right? And we will take up the next type of classifications of signal and some sort of more mathematical things that can be used on these continuous time signals and discrete time signals. We'll see with various examples. Thank you.
So can we get